everyone, and welcome to Session 2 of our Fundamentals of Remote Sensing webinar, focused on land management and wildfire applications. This is the second of 3 introductory sessions that we offer. Session 1 covers the fundamentals, and there's also a second Session 2 covering water resources. These sessions are intended to provide a basic overview of remote sensing and are recommended as a prerequisite for any future RSET webinar that you may attend, particularly for land management, wildfire, and water resources. These webinars are a little different than some of the others that RSET offers because they will not be offered live, nor will we provide certificates of completion. However, as I just mentioned, they may be required as prerequisites for future, more in-depth webinars. My name is Amber Kuss, and I will be presenting this webinar to you along with Cindy Schmidt. Before I get started with discussing the fundamentals of remote sensing, I wanted to give you some information about the RSET program. The goal of RSET is to increase the utility of NASA Earth science and model data for policymakers, regulatory agencies, and other applied science professionals in water resources, disasters, health and air quality, and land management. We offer several kinds of trainings, including online trainings and in-person trainings. To date, we have conducted 53 trainings with more than 4,000 participants from many different organizations and countries. RSET currently has 3 primary focus areas for training: health and air quality, water resources and flood monitoring, and land management, which includes wildfire applications. We also provide training to individuals and organizations that would like to develop their own online or in-person trainings. This introductory webinar is useful for water resources and land management applications. There will be different introductory webinars for health and air quality, so please check back on the RSET website listed on the previous slide for more information about that. Here's the outline for this session. Cindy Schmidt and I will be presenting on the satellites used for land management and wildfires. We will provide the basics of land cover mapping and outline land cover and fire detection products. We will then discuss the basics of detecting land cover change, and finally give you some information on 2 vegetation indices, NDVI and EVI. Next, we are going to discuss the specific satellites and sensors. We will start with a brief overview of the primary sensors for land management, Landsat, and MODIS. Then, talk about the characteristics of the data and where to obtain the images and products. First, I will discuss the MODIS instrument. MODIS is one of the key imaging instruments for NASA's Earth Observing System. It is designed to measure large-scale global dynamics across land, oceans, and the atmosphere. Flying on 2 satellites, Terra and Aqua, allows the MODIS sensor to capture imagery of the same area on Earth at different times of the day. MODIS imagery has varying spatial resolution depending on the product you're interested in, from 250 meters to 1 kilometer. The temporal resolution also varies from daily to 8-day, 16-day, monthly, and yearly composites. These data are available from 2000 to present. The original data format is HDF. However, there are now new sites that provide MODIS products as files such as GeoTIFFs that are easily digestible into geospatial software such as GIS. Spectrally, it has 36 bands, and the major bands of interest are in the visible and infrared. MODIS tiles, or the area over which MODIS image is obtained, is much larger when compared to Landsat, which we will discuss soon. This figure shows MODIS tiles compared to Landsat tiles. The red dots in the center of each of these smaller swaths represent the center of a Landsat image, and the brown squares represent the outline of a MODIS image. The lopsided squares that are in blue are one single MODIS image. So you can see that a MODIS covers an area that is much larger than Landsat. The MODIS naming convention can also be quite confusing. but it's important to understand the information within the names of the MODIS products when you've downloaded it from the website. So the first part of the name is actually the product number, shown here. It could be MOD, which means it comes from the Terra satellite. It could be MYD, which means it comes from the Aqua satellite, or MCD, which means it's a combined Terra and Aqua image. The next part of the name is the instrument it comes from, so MODIS. Next is the platform. Here it's Terra. It can also be Aqua or combined. The name indicates the parameter. In this case, it's surface reflectance. Then it provides the temporal resolution, 8-day, but it could also be a 16-day or monthly, for example. And then it provides the processing level, the spatial resolution, the projection, in this case sinusoidal, and the file type, grid. It's much easier to call MODIS products by their shortened name, shown in this table, such as surface reflectance as MOD09. The vegetation indices products are also called MOD13. This table also provides many of the products available that are useful for land management, such as land cover and land cover change, leaf area index, primary production, and others. As you can see, the temporal resolution also varies from daily to composites at 8-day, 16-day, monthly, and yearly. For more general information on MODIS, here are two websites that are really useful. The first is the Land Processes Distributed Active Archive Center, or LPDAC. The LPDAC operates as a partnership between the USGS and NASA. The second is the Earth Observing System Data and Information System, or EOSDIS. They have additional information on MODIS and multiple NASA products. They also have some great webinars themselves, so I recommend checking out this website for more information on MODIS and Landsat imagery and products. In addition to providing information about MODIS, both EOSDIS and LPDAC have many different datasets available for download. There are many places to obtain MODIS products, and a few of them are listed here. There is Echo Reverb, the MODIS land product subsets at the Oak Ridge National Lab DAC. There is the Global Land Cover Facility, GLOVIS, and the Fire Information for Resource Management System, or FIRMS, which delivers global MODIS hotspots and fire locations in near real time. Here are some additional places to find MODIS data, and these provide more visualization tools. First listed is WorldView, which is a tool that provides the capability to interactively browse and download global satellite imagery. Currently, there are limited MODIS land products available. You can find fires, land surface temperature, and snow cover on that website. SEVERE, a joint NASA-USAID capacity building program, has a global visualization mapper that enables you to visualize MODIS and other data globally. MRT Web will be discussed next. Historically, MODIS land product tiles have been distributed in a standard 10 by 10 degree extent with a sinusoidal projection in HDF format. There are now new MODIS data discovery and delivery services through MRT Web. MRT Web enables you to visualize, select, mosaic, subset, reproject, and reformat MODIS land products. Next, I will talk about the Visible Infrared Imaging Radiometer Suite, or VIIRS. Like MODIS, VIIRS is a multidisciplinary sensor providing data for ocean, land, aerosol, and cloud research and operational uses. VIIRS was launched on board SUMI NPP on October 28, 2011. The spatial resolution is 375 to 750 meters, depending on the product, with similar temporal resolution as MODIS. Therefore, data are collected daily, and there are 8-day, 16-day, monthly, quarterly, and yearly composites. The SUMI MPP satellite is also in the same orbital plane as the A-Train, which includes satellites such as CloudSat, Calypso, Terra MODIS. but it's at a higher altitude. It is a sun-synchronous at 824 meters with a local equator crossing time of approximately 1330. There are 22 bands measured by VIIRS. This includes bands in the visible spectrum, such as red and blue, as well as bands in the infrared. The near-infrared bands have been shown to be used particularly for applications such as wildfires. There are a number of ways that MODIS and VIIRS differ, both in the inherent spectral and spatial characteristics of the sensors, as well as in the algorithms being used to develop the products from the raw data, and the distribution of the data. NASA has been working closely with NOAA to investigate and correct algorithm issues. The LANPEAT at Goddard has been reprocessing VIIRS data and making versions available in common formats, very importantly with georegistration. While VIIRS is similar to MODIS, there are many differences in the spectral and spatial characteristics, as well as with the data processing and data delivery. They have similar but not identical spectral characteristics, with two of the bands in VIIRS as non-functional. VIIRS has improved spatial resolution at the edge of the swath, but has a lower resolution for the visible and infrared bands. Some of the standard products for VIIRS are different than MODIS. For example, there is no top-of-canopy NDVI environmental data record. There are differences in the algorithms used for cloud and aerosol filtering, and in the way the raw data are processed. Data distribution is also different between the two. There are a variety of land products produced in conjunction with NOAA. The most useful for land management is the active fires product, albedo, land surface temperature, and the vegetation index. The VIIRS Vegetation Index Environmental Data Record, or the VIEDR, is a swath product generated every day at the spatial resolution of 375 meters over land. The VIEDR consists of two VIs, the Normalized Difference Vegetation Index, or NDVI, derived from the top of atmosphere reflectances, and the Enhanced Vegetation Index, or EVI, derived from atmospherically corrected top of canopy reflectances. To find the VIIRS products, you can search the Comprehensive Large Array Data Stewardship System. This is hosted by NOAA and provides access to many different data products in addition to VIIRS. The website is shown here. All VIIRS land products can also be acquired from the Level 1 and Atmospheric Archive and Distribution System, or LADS web website. It includes the most recent products generated by NASA in HDF4 format. This is an example of how VIIRS Top of Canopy Enhanced Vegetation Index has been used to document the changing vegetation conditions in California during one of the worst droughts in history. The blue areas indicate areas of green vegetation, such as these shown here, while the dark brown areas are not vegetated. You can see gradual decreases in the vegetation from 2013 to 2015. In 2015, the dark blue / green color you see here indicates irrigated cropland. Next, I will be discussing the Landsat satellites. Landsat was first launched in the early 1970s. The data from the early Landsat sensors were called multispectral scanner imagery, or MSS. Those data have a lower spatial resolution than Landsat data, than the data you can obtain today. The MSS data are 79 meters, and the current Landsat data are mostly 30 meters. Most recently, Landsat 8 was launched in February of 2014. We have this continuous data at fairly high resolution, which is very useful for examining land surface changes over time. Just recently, all of these data were made freely available by the USGS. There is also a Landsat Global Archive, which we'll mention later. This slide provides some information on the spectral characteristics of Landsat. Landsat was designed primarily to detect visible and infrared light that's reflected from the Earth's surface. This graphic at the bottom shows you that these data are collected in different bands, shown here. And each of these bands represent a range of wavelengths. For example, bands 1, 2, and 3 detect data from the visible light range. You can see in the graphic here that band 1 is primarily blue-green, but it's called blue. Band 2 is green-yellow, but it's called green. And band 3 is red. Band 4 is the near infrared. Band 5 is the mid-infrared. Band 6 is the thermal band. And band 7 is another mid-infrared band. There's also a panchromatic band, which has a higher resolution of 15 meters, as opposed to the 30-meter multispectral bands. The panchromatic band works just like a black and white film. Instead of collecting visible colors separately, it combines them into one channel. Because this sensor can see more light all at once, it's the sharpest of all the bands. This table provides each band, the wavelength for each band, and the spatial resolution of each band. Remember, spatial resolution refers to the size of each pixel represented in square meters on the Earth. The bands are all the same with the exception of the thermal bands, which are a little coarser resolution than the rest. Landsat 8, the sensor that was recently launched, is a little different and has some additional bands that were not available in Landsats 4 through 7. There's an additional band 1 that is a coastal aerosol band that's designed to focus on nearshore environments and to penetrate the water a bit and to look at aerosol particles in the air. All the other bands are the same until you get to band 9, which is a cirrus band designed to look at clouds. And then there are two thermal bands, bands 10 and 11. The thermal bands are collected at 100 meters but are resampled to 30 meters to match the rest of the bands. This figure shows the differences in band coverage between Landsat 7 and Landsat 8. It also provides information about the atmospheric window that allows the sensors to obtain data in those spectral ranges. These windows represent the wavelengths at which electromagnetic radiation will penetrate the Earth's atmosphere, and thus can be observed by our sensors. Notice that while the bandwidths are similar for the two Landsat sensors, particularly in the visible range, they are not identical. Therefore, it's important to understand these differences when applying the same processes to each image from two different sensors. There are multiple websites where you can find information on and obtain Landsat images. I think it is oftentimes confusing because many of the sites function in the same way. In general, people tend to use the sites that they're most familiar with. However, it's probably a good idea to take a look at the various places where you can obtain these data and see what you prefer in regards to the way the data are visualized and how you can download the imagery. Here are a few examples of where you can obtain Landsat imagery with the website links below. First, we have the Landsat Look Viewer. This is one site where you can only get Landsat data. It's also a nice site to look at the quality of the data. Glovis is a really quick and easy online search tool and has different kinds of data such as MODIS. The Global Land Cover Facility has all of the Landsat data as well as ASTER data. The Earth Explorer is also easy to use to download different types of data in addition to Landsat. The nice thing about Earth Explorer is that you can use a shapefile or KML file to help locate your area of interest. You can also obtain data from the web-enabled Landsat Data Portal, or WELD, that provides Landsat data for 2003 to 2012 for the continental US and Alaska, and globally for 2009, 2010, and 2011. The WELD data are terrain-corrected and radiometrically calibrated, so users don't have to convert the Landsat digital numbers to reflectance. The USGS also has been working on the Landsat Global Archive consolidation, and this figure on the right here shows you where there are more in red or less in blue Landsat acquisitions over the over the scale of Landsat's lifetime. Finally, the Global Land Survey data is not a data portal, but it's a global collection of cloud-free Landsat images from 1975 to 2008. There's also time series available from 1975, 1990, 2000, 2005, and 2010 that are useful primarily for change detection. These data products can be acquired through some of the portals mentioned earlier. I will now hand it over to Cindy, and she will discuss land cover mapping with satellite imagery.
Hi everyone, I'm Cindy Schmidt and I will be first discussing land cover mapping with satellite imagery. The process of land cover mapping involves turning satellite data into thematic information about the region. The primary method of doing this is called image classification. On the left is a Landsat image of Lake Tahoe and its surrounding forests. However, the Landsat image cannot tell you whether the lake is actually water or the forest is actually forest. The classified image on the right shows how the pixel information in the satellite imagery can be transformed into land cover types. In order to understand how image classification works, we need to discuss the spectral signature of objects. As you recall, electromagnetic energy radiates from the sun in different wavelengths. Satellite sensors measure radiation that is either reflected or emitted from objects on the Earth's surface. Those objects reflect radiation differently, as shown in this graph. In the graph, the x-axis represents both wavelength, short to long from left to right, and the corresponding Landsat bands. And please note that these are Landsat 4, 5, and 7 and not Landsat 8. The y-axis represents the amount of reflectance of radiation for different land cover types. Vegetation reflects both green and near-infrared wavelengths, while soil reflects a little higher in the shortwave infrared wavelengths. These are called spectral signatures. On the left, we see a graph of spectral signatures for soil, vegetation, and water. You can also see the corresponding Landsat bands to the wavelengths that are on the x-axis. In order to understand how image classification works, we need to look at the relationship between the spectral signatures and the bands in a little different way. In the graph on the right, we've plotted the band 3, the red wavelengths, against band 4, near infrared. Looking back at the graph on the left, if we just look at water, you will notice that the percent reflectance is low in both band 3 and band 4. If you plot that information on the graph on the right, water will appear in the lower left-hand corner, low band 3 and low band 4. Going back to the graph on the left, if you look at vegetation, you will notice that vegetation has low reflectance in band 3, but high in band 4. Translating that to the graph on the right means that vegetation belongs on the lower right-hand side, low band 3 but high band 4. Lastly, dry soil has slightly higher reflectance in band 4 than band 3, but the values are in between water and vegetation. You can see where soil falls in the graph on the right. So now you can see that the 3 land cover types are in 3 very different locations on the graph. Image processing software can be used to separate out the different land cover types using this method. All pixels that have similar reflectance characteristics to each of the land cover types will be labeled the same. Of course, Landsat imagery has more than just 2 bands, so the software uses any number of bands that you choose. You can also specify the number of land cover classes that are in your study area. In this example, there are only 3 land cover classes: water, vegetation, and dry soil. But in reality, of course, there are many more. There are many ways of doing image classification, but 2 common ones are called supervised and unsupervised classification. We will not go into any detail about these methods, but if you are interested, I encourage you to read more about it or take an image processing class. One of the most common questions we get is, can you distinguish between different vegetation types? The answer is, it depends. Using a multispectral sensor like Landsat, green vegetation looks very similar, and it is often very difficult to distinguish between different vegetation types. However, there are various methods that may help. One is to use a hyperspectral imager such as Avaris, which uses an airborne platform. Hyperspectral imagery enables you to detect more subtle differences between vegetation types. Another common method is to use ancillary information such as elevation, slope, and aspect with Landsat imagery to help distinguish vegetation types. This method uses the assumption that some different vegetation types will grow in different regions. For example, some species of conifers only grow at high elevations and some only at lower elevations. Another very common method is to use a spectroradiometer in the field to collect specific information about the spectral reflectance of different vegetation types. This is typically used with hyperspectral imagery to precisely identify spectral signatures. Next, I will describe land cover products derived from satellite data that you can download. Land cover products for just the U.S. include the National Land Cover Database, gap analysis data, and Wildfire. Global products include the FAO Global Land Cover Network and various forest change products. Next, I will be discussing these products. The NLCD products include land cover type, percent impervious surface, and percent tree canopy cover at 30 meter spatial resolution. The database is available for 1992, 2001, 2006, and 2011, and is created using a 16 class classification scheme. The database is based primarily on Landsat data, along with other data sources such as topography, census, and agricultural statistics, soil characteristics, wetlands, and other land cover maps. The data are freely available at the website listed here. The USGS Gap Analysis Program has three primary goals. One, to identify conservation gaps that help common species common. Two, to provide conservation information to the public so that informed resource management decisions can be made. And three, to facilitate the application of gap data to specific resource management activities. To do this, GAP maps the land cover of the U.S., maps predicted distributions of vertebrate species, maps the location, ownership, and stewardship of protected areas, and documents the representation of vertebrate species and land cover types in areas managed for the long-term maintenance of biodiversity. The land cover is mapped at 30 meter spatial resolution using Landsat satellite imagery as well as other data sets such as digital elevation models, soils, geology, stream, and wetland location. Other data include point locations for rare plant communities and fire and tree harvest information. The GAP data can be found using the Land Cover Data Viewer found on the website listed here. The Wildfire mission is to improve fire and natural resource management. This program provides a national inventory of geospatial data, vegetation composition and structure, fire behavior and effects, fuel loading models, and fire regime conditions of the entire U.S. from 2006 to present. Data products are organized into groups, which include disturbance, vegetation, fuel, fire regime, and topographic. Data products are delivered at a 30 meter pixel resolution for landscape scale analysis. The products are great for national and regional planning because they are updated every 2 years to reflect changes on the landscape over time. You can find these data at the website listed here. The Food and Agriculture Organization has developed a global land cover map using the best available national, regional, and/or subnational land cover databases. They used a specialized system and fusion techniques to harmonize the various databases and developed a procedure to update the database when new data sets become available. The database is comprised of 11 land cover layers. The database is currently in beta release, but can be downloaded from the website listed here. The MODIS yearly land cover product incorporates 5 different classification schemes that describe land cover properties derived from observations spanning a year. The primary classification scheme identifies 17 classes defined by the International Geosphere-Biosphere Program, which includes 11 natural vegetation classes, 3 developed land classes, and 3 non-vegetated land classes. The data have a spatial resolution of 500 meters and can be downloaded from the EOSTIS Reverb website. Next, I will talk specifically about fire detection products. The MODIS Thermal Anomalies and Fire product provides snapshots of both active burning fires and burned areas globally. MODIS's mid-infrared band allows the instrument to identify the locations of thermal anomalies, thus active fires. This product provides unique dimensions such as a fire mask and a fire pixel table for each fire pixel. The fire pixel table characterizes 19 attributes for fire pixels, including maximum fire radiative power. FIRMS provides near real-time active fire mapping and historical data available for download. You can get or visualize the data in various ways, including email alerts, download directly, or visualize in web-based tools. You can get more information on the FIRMS data from the website listed here. This MODIS product detects the approximate date of burning and maps the spatial extent of recent fires by analyzing daily surface reflectance and using a model-based change detection algorithm to locate rapid changes on the Earth's surface. This is a monthly gridded 500-meter product that you can acquire at the website listed here. The image shows the extent of a fire that occurred in 2007 in Georgia and Florida. The colors represent the different dates of burning between April and May 2007. A relatively new product is the VIIRS Active Fire product. It provides near real-time active fire locations, currently at 700 meter or the M band, with a beta version of a 350 meter or I band product. This product is developed using an algorithm that detects thermal hotspots on a daily basis. The VIIRS data are also searchable on a user-friendly mapping interface and available for download as a GeoTIFF, ASCII, or KMZ file. You can access these data and visualize them as well at the website listed here. Next, I will be discussing how to detect land cover change with satellite imagery. Detecting change of the Earth's surface features is extremely important for understanding relationships and interactions between human and natural phenomena. The questions that can be answered using remote sensing include: where and when has change taken place? What is the quantity of the change and what is the nature of the change? And lastly, what are the cycles and trends of the change over time? These images show the growth of Santiago, Chile between 1975 and 2013 from the Landsat sensor.
No, just remote sensing.
These are just a few of the many applications of change detection using satellite imagery. The images on the right show bark beetle infestation in Colorado between 2005 and 2011. In 2005, there was little to no infestation as shown by the green vegetation. In 2011, the brown areas indicate the trees that had been killed due to the beetle infestation. Many change detection techniques using remotely sensed imagery have been developed, and I will be describing these 4 of them to you. One of the most basic methods for detecting change using satellite imagery is called heads-up digitizing. In this method, you display the imagery using GIS or image processing software and digitize a polygon around the areas of change. In these images, the Santiago urban area was digitized for the 2 different years. The size of these polygons can then be measured to quantify the amount of change that has occurred. These traditional methods use the change in the pixel values to document change. The image subtraction method works by simply taking a single band from 2 different dates of imagery and subtracting one from the other that results in a change image. The change image consists of positive and negative values where change has occurred and 0 values where no change has occurred. Image classification requires that both dates of image stacks consisting of multiple bands be classified first to identify land cover classes by pixel. Then, using a pixel by pixel comparison, change between land cover types can be detected. For both these methods, it is very important that the images are precisely registered to each other. For both methods, you need GIS or image processing software. You also need to know the area well enough to interpret the change because the software will not do that for you. Recent developments in change detection methods take advantage of the entire freely available Landsat archive by using monthly or annual time series to look at changes or trends. While in the previously described methods, you would only use 2 image dates. In this method, you could use 20 or 30 image dates. This method allows the capture of short duration disturbance events as well as long-term disturbance trends. This approach is founded on the recognition that change is not simply a comparison between conditions at 2 points in time, but rather a continual process operating at both fast and slow rates on the landscapes. There are several different algorithms emerging, and this is an example of LandTrender developed by Kennedy et al. At Oregon State University. The results of this algorithm include the magnitude of change that identifies the percent of tree cover loss, the duration of the disturbance, and the year of onset of the disturbance. Next, I will be discussing the use of remote sensing for deriving vegetation indices and phenology. Normalized Difference Vegetation Index, or NDVI, is one of the most commonly used vegetation indices. It is based on the relationship between the red and the near-infrared wavelengths. When sunlight strikes plant leaves, the chlorophyll in those leaves strongly absorbs visible light, primarily blue and red, and the cell structure of the leaves reflect green and strongly reflects near-infrared light. This is portrayed in this graphic on the top as well as the graph below it. The 2 key wavelengths for NDVI are the red and near-infrared. In this graph, you can see where the red is being absorbed and has low reflectance, and the near-infrared is highly reflective. As I just mentioned, NDVI is the relationship between the red and the near-infrared wavelengths. The actual formula is specified here. It's the near-infrared minus the red divided by the near-infrared plus the red. The values of NDVI for an individual pixel range from -1 to 1. Any pixel between -1 and 0 means no vegetation, and pixels close to 1 indicates the highest possible density of green leaves. The picture on the right shows that healthy green vegetation absorbs most of the visible light, where only 8% is reflected, and reflects a large portion of the near-infrared light, where 50% is reflected. Unhealthy, sparse, or senescing vegetation reflects more visible light, in this case where 30% is reflected, and less near-infrared light, where 40% is reflected. You can see the difference in the resulting NDVI values below the image. The green vegetation has a value closer to 1, while the brown vegetation has a value closer to 0.
The data is really accessible.
This NDVI image was derived from Landsat satellite data and shows vegetation density across the Greater Panama Canal watershed.
And the brown.
In this image, the darker the green area, the more green vegetation is
Many
present.
applications, for
The
example,
rainforests of Panama stand out clearly as the dark green swaths on either side of the Panama Canal. These forests harbor a very diverse community of plants and animals and also help reduce erosion and sedimentation to the canal. The light green and brown colors are more sparsely vegetated pastures and croplands. The white area shows areas of human development. Plant phenology is the annual dynamic of vegetation greenness and can be tracked using vegetation indices. In the graph on the top, you can see the progression of vegetation dynamics as seasons change. In North America, early in the year, which is winter, there are little to no leaves on the trees, resulting in low NDVI values. When spring arrives, the vegetation greens up and NDVI increases until it peaks in the summer. Then, as vegetation senesces and loses their leaves, the NDVI declines. The image below shows the difference in greenness in the winter on the left versus the summer on the right in North America.
Okay.
NDVI can also be used in relation to drought monitoring and in conjunction with a variety of other data products. This is an example of an NDVI anomaly map from September 2002 for the African continent. The brown areas represent negative vegetation anomalies and the green areas represent positive vegetation anomalies. Using time series of data, anomaly maps can be generated to show differences in vegetation densities.
843.
The Enhanced Vegetation Index, or EVI, is another vegetation index available from the MODIS sensor. The NDVI is more chlorophyll sensitive, while the EVI is more responsive to canopy structural variations, including leaf area index and canopy type. One problem with the NDVI is that it saturates over high biomass areas. The EVI was developed to optimize the vegetation signal with improved sensitivity in high biomass regions and a reduction in atmospheric influences.
What was going on? Why did it...
Both NDVI and EVI from MODIS are available in several different temporal composites, ranging from 16 days to monthly, and spatial resolutions ranging from 250 meters to approximately 5.5 kilometers. The names of the products are listed on the right. You can acquire these data from the websites listed here.
Because they put your number.
No, I just put it.
Here is an example of how NDVI and EVI are being used. In collaboration with the Desert Locust Information Service, the International Research Institute for Climate and Society is developing products to estimate ecological conditions and rainfall events in the desert locust recession area. They are focusing on locusts because adult desert locusts can form swarms that can fly or be carried by wind over great distances. These swarms can wipe out crops located hundreds of kilometers from their places of origin and create starvation conditions in regions that are already financially challenged. The products include a MODIS analysis tool where you can visualize both NDVI and EVI over time to observe changes in greenness. You can zoom into a particular area and then obtain a graph of the change of NDVI or EVI over time. This concludes our second session on the fundamentals of remote sensing. We want to thank you for listening to our webinar, and please feel free to contact us if you have any questions or comments. For land management and wildfire training inquiries, please contact me, Cindy Schmidt, or Amber Kuss. For water resource inquiries, please contact either Amita Mehta or Brock Blevins, and for general RSET inquiries, you can contact Anna Prados. For information about all our webinars and other trainings, please go to our website listed at the bottom of this page. Thanks again for your participation, and goodbye until next time.